Hello everyone, welcome to this learning video. I am Shubham from MSc Chemistry first year. This video is specially designed for visually impaired students. Unit 2nd Inorganic Chemistry Reaction Mechanism for Octahedral Transition Metal Complexes Part 1 Inert and labile complexes. In coordination chemistry, coordination showed different reactivities toward ligand substitution. Some complexes react very fast when a ligand is replaced by another ligand, while some react extremely slow even under strong conditions. Therefore, complexes are divided into two categories: labile complexes, inert complexes. A complex is called inert, labile, if ligand substitution occurs with a half-life of less than 1 minute. A complex is called inert if its ligand substitution is half-life is greater than 1 minute. Thermodynamic and kinetic stability. A complex have large stability constant but still be labile if its ligand substitution happens very quickly. For example, CuH2O6 under the bracket whole charge 2 plus is the thermodynamically stable but labile. A complex may be thermodynamically unstable but kinetically inert if its ligand substitution is slow. Example, low spin copper 3 complexes. Mechanism for ligand replacement reactions. First, dissociative mechanism. In this mechanism, leaving ligand departs first, forming a 5-coordinate intermediate. After that, the incoming ligand attaches. In step 1, complex loses a ligand and make Ml6 gives Ml5 plus L negative. In step 2, incoming ligand coordinates to 5-coordinate intermediate. Ml5 plus L dash gives Ml5 L dash complex. Rate law. Rate law depends only on the concentration of complex, not on the incoming ligand. Hence, rate is equal to K into Ml6, where K is the rate constant. Conditions favoring large metal centers 4D, 5D, weak metal ligand bonds, high steric crowding in complexes, labile ligands. Intermediate geometry. The 5-coordinated intermediate generally have trigonal bipyramidal geometry. Second, associate mechanism. The incoming ligand first associate with complex generating 7-coordinate intermediate followed by departure of another ligand. Step 1. Incoming ligand approaches and binds. Ml6 plus L dash gives Ml6 L dash. Step 2. One ligand leaves to restore coordination number. Ml6L dash give Ml5L dash plus L. Rate law. K into Ml6 into L dash. Conditions favoring small metal ions, high positive charge, strong field ligands, square planar complexes. Intermediate geometry. 7-coordinate intermediate often takes pentagonal bipyramidal geometry or transition state like adduct. Third, interchange mechanism. When bond breaking and making happen simultaneously without forming detectable intermediate, the mechanism is called interchange. First, interchange dissociative ID. Bond breaking is more significant. No detectable intermediate but transition state resembles the dissociative form. Second, interchange associative IA. Bond formation with incoming ligand is more significant. Transition state resemble an associated form. Rate law. Rate is equal to K into Ml6 for interchange dissociative mechanism. Rate is equal to K into Ml6 into L dash for associate mechanism. Formation of complexes from aqua ions. When a metal salt is dissolved in water, the metal ion does not exist as a bare cation. Instead, it immediately becomes hydrated by water molecules and form aqua complexes such as MH2O6, whole charge and minus. These aqua complexes undergoes substitution reaction when other ligands replace water molecules. Thus, formation of all coordination compounds in solution begins with the formation of aqua ions. Aqua ions are hydrated metal ions where water acts as ligand by donating a lone pair from oxygen to metal ion. This process is extremely fast and essentially diffusion controlled. General form. For octahedral complexes, MH2O6 whole charge and negative. For some large or low charge metals, 4 coordinate tetrahedral aqua complexes may form. Examples: AlH2O6 whole charge 3 negative, FeH2O6 whole charge 2 positive. General reaction: MH2O6 whole charge N plus Xl gives MH2O6 minus X Lx whole charge N positive plus XH2O. This is known as anation because an anionic or neutral ligand replaces water. For labile aqua ions, these complexes substitute water quickly and follow dissociative mechanism. Example: copper into H2O6 whole charge 2 plus 4NH3 gives CuNH34 H2O2 whole charge 2 plus 4H2O. For inert aqua ions, these form very stable aqua complexes, so replacing water is slow. Mechanism usually is dissociative. Ligand displacement reactions in octahedral complexes. First, acidic hydrolysis. Acidic hydrolysis is a ligand substitution reaction in which a coordinated ligand is replaced by water molecule, specifically under acidic conditions. This means equation of promoted by H positive, not by base. General reaction: Ml5X whole charge N positive plus H3O positive gives Ml5OH twice N plus 1 plus X negative, where X negative is equal to ligand which leaves and is replaced by water. This process is slow for inert complexes and often require heating. However, even labile complexes show increased substitution rate in acidic medium. Mechanism: interchange dissociative. First, partial MX bond weakens, then the metal halide bond weakens due to first protonation of X negative, solvation of X negative by water, electrostatic repulsion decreasing. Second point, departure of X negative. The leaving ligand X negative exits the coordination sphere. Ml5X whole charge N positive gives Ml5N plus 1 plus X negative. Coordination of water. Ml5N plus 1 plus H2O gives Ml5H2O whole charge N plus 1. Net reaction: Ml5X whole charge N plus H3O positive gives Ml5H2O whole charge N plus 1 positive plus X negative. Rate law. Rate is equal to K into complex, where K is the rate constant. This indicates dissociative or ID mechanism. For acid catalysis, rate law is equal to K into complex into H positive. Basic hydrolysis. Basic hydrolysis refers to ligand substitution reaction that occurs in presence of OH negative, where hydroxide ions act as nucleophile, a base, and sometimes a catalyst. General reaction: Ml5X N positive plus OH negative gives Ml5OH N positive plus X negative. First, by SN1CB mechanism. Step 1. Reprotonation. A coordinated water ligand loses a proton OH negative which acts as a base. This forms a conjugate base complex which is more reactive. Step 2. X negative leaves. Loss of leaving group from conjugate base. Ml5OH N-1 gives Ml5 N-1 plus X negative. Step 3. Finally, vacant site is filled. Ml5 N-1 plus H2O gives Ml5H2O whole charge n minus 1. Or SN2 mechanism. Incoming OH negative attacks metal, transition state is formed and leaving group exits. Note: basic hydrolysis is a ligand substitution in presence of OH negative in octahedral complexes. Most inert complexes show SN1CB mechanism where OH negative first removes a proton forming a conjugate base, which then undergoes slow ligand dissociation. Labile complexes may follow SN2 mechanism where OH negative directly attack the metal. Rate is affected by pH, metal oxidation state, leaving group and ligand field. Anation reactions. Anation is a ligand substitution reaction in which a water ligand is replaced by anionic ligand A negative in a metal complex. General reaction. For octahedral complex, Ml5H2O whole charge N positive plus A negative gives Ml5A whole charge N minus 1 plus H2O, where A negative is equal to Cl negative, Br negative, I negative, Cn negative, and L is equal to ligands like NH3, H2O, En. Examples. First, anation of pentaamine cobalt 3 reaction is CONH3 5H2O whole charge 3 plus Cl negative gives CONH3 5Cl whole charge 2 plus H2O. Second, chromium 3 water exchange CrH2O5 H2O whole charge 3 positive plus SCN negative gives CrH2O5 SCN 2 positive plus H2O. Replacement with nitro group Ml5H2O whole charge N positive plus NO2 negative gives Ml5NO2 whole charge N minus 1 positive plus H2O. Characteristics usually follow dissociative mechanism, rate independent of A negative in dissociative pathway. H2O is a leaving ligand. An anionic ligand replaces neutral ligand. Factors affecting ligand substitution in octahedral complexes. First, nature of metal ion. Higher oxidation state gives greater Ml bond length, hence more inert. Size of metal ion. Large metal ion makes weaker bonding, hence labile complexes. Third, higher CFC gives strong bonding, so slow substitution reaction. Nature of ligands. Ligand field strength. Strong field ligand have more crystal field stabilization energy, hence slow substitution. Weak field ligands give faster substitution. Donor atoms. Soft donor binds strongly to the soft metals, hence slower substitution. Leaving group ability. Leaving group ability is as in decreasing order: I negative, then Br negative, then Cl negative, then H2O, then NH3. Hence better leaving group, so faster substitution reaction. Steric factors. Bulky ligands. Difficult to approach of incoming ligands, hence lower reaction. Charge on complex. Higher positive charge, stronger attraction for incoming nucleophile, faster associative pathway. So higher negative charge gives repulsion of nucleophile, so slower reaction. Optical rotation. Optical rotation is a rotation of plane polarized light when it passes through a chiral substance. If a compound has chirality, it interacts differently with left and right circularly polarized light. This difference causes rotation. Type of optical rotations: dextrorotatory, levorotatory. Dextrorotatory rotates plane polarized right to right. Levorotatory rotates plane polarized light to left. Specific rotation. The standardized way to measure optical rotation is alpha is equal to alpha observed divided by IC, where alpha observed is equal to observed rotation, I is equal to path length, C is equal to concentration gram per ml. Cotton effect. Cotton effect belongs to circular dichroism and is especially important for chiral inorganic complexes. Optically active organic molecules. The Cotton effect is change in optical rotation of chiral compounds near absorption band. When plane polarized light near an electronic transition wavelength passes through a chiral sample, rotation shows a sharp increase, which is positive Cotton effect, a sharp decrease, negative Cotton effect. Near lambda max, this variation is called Cotton effect. It occurs because a chiral molecule absorbs left circular and right circular polarized light to different extent. If left circular polarized light is greater than right circular polarized light, so negative Cotton effects. If right circular polarized light is greater than left circular polarized light, then positive effect. Importance: determine absolute configuration, identify chiral metal complexes, study electronic transitions, circular dichroism spectroscopy. Racemization of tris-chelate complexes. Tris-chelate complexes are of type MAA3 whole charge and positive, where AA is equal to bidentate ligands such as ethyl diamine, oxalate, B pi Y, PHEN, which exist as two enantiomers. Delta is equal to right-handed helix and lambda is equal to left-handed helix. These two forms are non-superimposable mirror images. Racemization means interconversion of lambda to delta through mechanism that removes chirality. Why racemization difficult in tris-chelate complexes? Because three bidentate ligands wrap around metals very tightly, hence very unstable, so right octahedral geometry is made. Higher chelate stability, which is called chelate effect. Factors affecting racemization. First, metal ion. Labile metals do faster racemization like Ni2 positive, Cu2 positive, Fe2 positive. Inert metals do very slow racemization. Chelate ring size: 5-membered ring, slow racemization, 6-membered ring, faster racemization. Flexible ligands do faster racemization, rigid ligands do slower racemization. Higher temperature provides energy for twisting, faster racemization. Polar solvents stabilize intermediates, faster racemization. Example: COEN3 whole charge 3 plus, very inert, racemizes only at high temperature. Cr oxalate 3 whole charge 3 negative, hard to racemize because oxalate is rigid. FeBpy thrice whole charge 2 positive, more labile, racemize faster. Electrophilic attacks on ligands. Electrophilic attack on ligand refers to reaction where electrophile does not attack the metal center directly but instead attack the coordinate ligand. The ligand reacts because coordination modifies its electron density, reactivity and orientation. Reasons: increase electron density on ligands, more nucleophilic ligand. Polarize the metal ligand bonds, expose certain atoms of ligand to attack. Restrict certain ligand conformation, directing electrophile to specific sites. General reaction: the electrophile attack can be represented by metal ligand bond plus electrophile gives MLE whole charge and positive. Mechanism: step 1, activation of ligand by metal. Metal changes electron density on ligand, make ligand more nucleophilic or more polarized. Approach to electrophile. Electrophile attack electron rich sites of ligand. Attack can be directed by metal influence. Formation of new bonds. Ligand electrophile bond forms. Metal ligand bond may weaken or remain intact. Examples: protonation of NH3. CONH3 6 3 positive plus H positive gives CONH3 5 NH4 3 positive. Nitration of arene chromium complexes. Eta 6 C6H6 CrCO3 plus NO2 positive gives eta 6 C6H5 NO2 CrCO3. Protonation of CO ligand. MCO plus H positive gives MCOH. Factors affecting thermodynamic stability of metal complexes. Thermodynamical stability of a complex refers to how easily a complex can exist without dissociating into component, metal ion and ligands. It depends on overall free energy change del G for formation of complex. Mn plus XL gives MlXn positive complex. If del G is highly negative or formation constant, Kf is large, complex is thermodynamically stable. Kf is equal to Ml6n positive divided by Mn positive into L. Larger Kf more stable complexes, smaller Kf less stable complexes. Stepwise formation constants. Mn positive plus L gives Mln positive. K1 is the rate constant. Mln plus L gives Ml2n plus K2 rate constant. Ml2n plus L gives Ml3n plus K3 rate constant. Overall stability complex beta n is given by K1 into K2 into K3. Usually K1 is greater than K2, K2 is greater than K3 and so on because crowding and repulsion increases with each added ligand. Factors affecting stability. Nature of metal ion. Charge and size. Higher charge, smaller ionic radius, so strong electrostatic attraction, more stable complexes. Example: Fe3 plus forms more stable complexes than Fe2 plus. Electronic configuration is half filled or fully filled orbitals often give extra stability. Example: Ni2 plus D8 is greater than CO2 plus D7 configuration. Nature of ligand. Basicity. More basic ligand donates electron easily, strong bonding, so higher stability. Example: NH3 is greater than H2O is greater than F negative. Chelate effect. Multidentate ligands like EDTA EN form ring structures with metals, increase stability. Example: NiEN3 2 positive is more stable than NiNH3 6 2 positive. Resonance and pi bonding. Ligand with pi acceptor ability like CO, Cn negative stabilize metal via pi back bonding. Steric effects. Bulky ligands cause crowding, hence stability decreases. Smaller ligands fit better, hence they form stable complexes. Solvent effects. Polar solvent stabilize ions and hence may decrease complex stability and since dissociation is easier. Example: NiNH36 whole charge 2 positive and NiTBu NH26 whole charge 2 positive. So tertiary butylamine is bulky, hence steric hindrance is more, so less stable complex. Hence NiNH36 2 positive is more stable than NiTBu NH26 2 positive. Cu2 plus 4NH2 gives CuNH34 2 positive complex. In water, water strongly hydrates Cu2 positive ion, stabilize the free ion, less tendency to form complex, hence lower stability. In ethanol, Cu2 plus is less stabilized, more likely to bind with NH3, higher stability. Entropy effect. Chelation increases entropy because several particles, metal plus multiple ligands combine to form one entity favorable for stability. If del S is equal to positive, stability increases. Crystal field stabilization energy. Complexes with higher crystal field stabilization energy are more thermodynamically stable. Example: for octahedral complexes, stability order often follows CFC. D3 configuration is always stable than low spin D5. Relation between thermodynamic and kinetic stability. Thermodynamic stability governed by del G, kinetic stability governed by activation energy. CONH3 6 3 positive are thermodynamically unstable but kinetically inert. NiH2O6 2 positive are thermodynamically stable but kinetically labile. Chelate effect. It depends on the following factors. Number of chelate rings, more stability. Number of donor atoms, NO donor form stronger chelates, metal ion size and charge. Small, highly charged metal, more stable chelate. Flexibility of chelate. Flexible ligands form chelate ring easily. Examples: CuNen3 2 positive and CuNH3 6 2 positive. Cu2 plus 6 NH3 gives CuNH3 6 2 positive. Cu2 positive plus 3N gives CuEn3 2 positive. NH3 is a monodentate ligand. Ethyl diamine is bidentate ligand. Hence CuEn3 more thermodynamically stable because each En form chelate ring and hence entropy increase and multiple bond make harder to dissociate. Resonance effect. Plus M ligands increase stability of metal with high positive charge because they donate more electron density to metal center. Minus M ligands stabilize low oxidation state through pi back bonding, which also increase thermodynamic stability. Example: FeCN6 4 negative, where Cn is equal to minus M and pi acceptor ligand forms very stable complex with Fe2 plus CFCe plus back bonding both high. Irving-Williams series. Describe the relative stability order of high-spin divalent octahedral metal ions complexes M2 plus of first transition state with same ligand. For M2 positive, series is like M2 plus is less than F2 plus, Fe2 plus is less than CO2 plus is less than Ni2 plus is less than CO2 plus, and CO2 plus is greater than zinc 2 plus. This means stability of complex increase from Mn2 plus to Cu2 plus and then slightly decrease at zinc 2 positive. Reason for this trend: ionic radius across 3D series, ionic radius decrease as atomic number increase. Smaller have higher charge density, so metal ligand bond becomes stronger. Mn2 plus is less than Fe2 plus is less than CO2 plus is less than nickel 2 plus is less than copper 2 plus and is less than zinc 2 plus. Hence contradiction of it strengthen Ml bond up to Cu2 plus. It reflects thermodynamic stability, not kinetic stability. Both CFC and ionic size contribute to this trend. Zinc 2 plus complexes are less stable because they lack CFCE. Cu2 plus is exceptionally stable due to John Teller distortion. Thank you.